Thank you very much. Good morning, ladies and gentlemen. It's a great pleasure and honor for me to give a talk here on this masterclass as a member of the Scientific Advisory Board. Today I want to speak about the diagnostics of ion beams for space propulsion and industrial surface processing, and especially, or in particular, I want to focus onto two diagnostics, what we call non-conventional diagnostics for the characterization of plasma surface interaction and also for the characteristics of ion beam sources. This is together with my colleagues Thomas Tordenberg, Alex Späthmann, Mathis Klette, Luca Hansen and Ruben Wiese, who are postdocs or PhD students in my group. So after a short motivation, I will focus on these two diagnostics which I mentioned, and that's the measurement of the energy and flux from a plasma or from an ion beam source to surfaces by so-called colorimetric probes, and the measurement of the momentum transfer, for instance during sputtering but also during ion beam operation, by special probes. Okay, if you have an interaction between plasma and a solid, maybe a solid for treatment as a substrate or the electrodes in a plasma source, or for diagnostics where you have to use a solid, a probe for instance, then always you have this interaction between the plasma and the solid surface. And on the one hand side you have the plasma, for instance as the source for the ion beams and space propulsion, and the plasma itself is very complex, as you know, or most of you know that of course. You have a lot of macroscopic knobs where you can influence or affect the plasma properties, like the gas pressure, the supplied power, the gas mixture, the geometry of the electrodes, the gas flow, the excitation frequency is a DC, RF or microwave, and so on. And all these macroscopic knobs at the end result in internal plasma parameters like the density of charge carriers, electron and ion densities, maybe degree of dissociation. You have reactive gases like oxygen, nitrogen, something like that. And of course in the energy distribution of the related species. And only in the case of a Maxwellian velocity or energy distribution you can speak about temperature, as you know, and then we speak about electron temperature, ion temperature and so on. And it's important to know the velocity or energy distribution functions of the species, because you want to tailor these energy distribution in order to get the right or the optimized interaction between plasma and surface, or have a high degree of ionization or excitation. On the other hand, you have the solid, the surface, which also can be affected by different macroscopic properties, like for instance the potential. You can have a positive or negative bias potential. By temperature you can heat or cool the surface. Is it crystalline or amorphous? What's about the crystal structure? And now you bring both of these complex systems, which also can result in internal or microscopic properties like adsorption rates, desorption rates, chemical sputtering, physical sputtering and so on. And now you bring together both of these complex systems, and then you know there is a sheath. There is a sheath in front of a surface, there is a solid interacting with a plasma, and through the sheath there is energy transport, there is momentum transport, and there is or might be a rather strong electric field in front of a substrate. And we have a lot of diagnostics for the plasma bulk and also for the surface properties, but we have only a very few diagnostics to get information about the sheath properties. So, and therefore we are always interested in this interaction, and especially in the energy and momentum flux between the plasma and the surface. And of course there exists a broad variety, a zoo of different plasma diagnostics. Most of you are using them, for instance for the charged species, the electrons and the ions, Langmuir probes, retarding field analyzer, Faraday cups. There is optical spectroscopy, either an emission absorption or ELIF or in quantum cascade laser absorption spectroscopy. There might be mass spectrometry, and even if you are interested in the energy distribution of the species, then we call it plasma monitoring or energy selective mass spectrometry. You can have the YEI probes for electrical characteristics of a discharge, and many, many others. And we like to add non-conventional diagnostics, for instance, the energy flux measurements, the force measurements, and the microscopic particle probes. I will not speak about the last point, which is interesting as well. So we use tiny microscopic particles in the sheaths. We confine them in a sheath and manipulate these particles which are charged in a sheath in order to get the force balance information about the electric field structure in front of the surface. I will just speak about these measurements, diagnostics, the energy flux measurements and force measurements. And they are interesting if you look at the moments of the velocity distribution function of the charge carriers or other species. Then of course the zero moment is the current. If you integrate about the velocity distribution of the species, the electrons or ions, then you get of course the current, the electric current or the current density. If you take the first moment, you get the force of these which act by these charged particles, but there might be additional forces, for instance the electric field force in the sheath. There is a force onto charged particles or uncharged particles due to the field, due to the electric field acting onto charged particles. And the second moment, again, you have to integrate about or over this quantity, then you get the power which is coming from the species or brought by the species to the surface. But again, there might be additional contributions to the power balance, like radiation, either from hot surfaces or from line radiation of the plasma. If there is a growing film, there is condensation and absorption heat, there are chemical reactions, exothermic or endothermic, there might be additional chemical power by sputter processes and so on. And all these quantities, the current, the force and the power, are related to this interaction and related to the internal plasma parameters, and it is interesting to measure them and to compare them by models. Okay, I will speak about the first diagnostics, the colorimetric or thermal probes. And I will want to motivate it from the view of thin film deposition, for instance. A few may know this so-called Thornton diagram. If you deposit thin films by sputtering or PECVD, plasma-enhanced chemical vapor deposition, or by other plasma-based processes, of course, then the property of the deposited film depends on the flux of the incoming particles, but also depends on the thermal balance or the thermal conditions of the substrate. If there is an amorphous or microcrystalline or crystalline growth of the film, depends on these conditions. And of course, here is the temperature of the substrate in units of the melting temperature. So one is the melting temperature, and the temperature is rather high, then you almost always get crystalline films due to mobility and phase transition in the film. In the growing film you get a crystalline film. But for some physics you want to have lower temperatures but also get a microcrystalline or crystalline film, and as you can see here, you can get it. If you change, for instance, the pressure or the energy of the incoming ions. So there is a local energy deposition by incoming ions, and these can, even at reduced substrate temperature, you can get local and in the thin film a higher energy deposition, which gives you already at lower temperature also a microcrystalline or a crystalline film. So there you can see an example where the energy influx is important. Or if you think about micro or nanoparticles, growing nanoparticles in a plasma, then at the surface of such a nanoparticle or microparticle you have a balance, an energy balance, due to incoming energy by kinetic energy of charge carriers, depending on the potential of this particle. There might be radiation from the surrounding. There might be molecule formation at the surface, there might be a neutralization of ions and electrons at the surface and so on. And there might be also film growth, and then at the end there is a balance resulting in the equilibrium temperature of these particles, which can be tried to measure in order to get information about the elementary processes at the surface. And such a particle is just a kind of a floating small probe. An example, many years ago we did growth of these carbonaceous nanopillars on a surface, maybe for optical or catalytic applications, but these pillars, like carbon nanotubes, they just grow on a footprint, and these footprints is metal, for instance iron or nickel or something like that. So we deposited a very, very thin nickel film of a few nanometers, and then without heating, external heating, just by playing with the plasma conditions, argon or argon hydrogen, we could melt these very thin film in order to get such kind of droplets or footprints where these carbonaceous columns are growing. And this is just done by playing with the plasma conditions. As you can see here, there's no other heating, but we changed the gas composition. So here this is the pure argon, which is an electropositive gas, and here we add hydrogen. And as you can see here, we get almost a factor of 2 in the energy influx just by addition of hydrogen. And why? The hydrogen is dissociated in the plasma, and at the surface, at these nickel films, the hydrogen recombines again to the molecules, to hydrogen molecules. And then the dissociation energy is released. And this is sufficient in order to influence or to melt these thin film and to produce the structure where the columns can grow. Again, this is an example how the energy influx from the plasma to the surface influences the surface conditions and the properties. So at the end we have contributions to the energy influx and a lot of contributions to the energy outflux. That means gain and losses of power or energy per time at the surface. So there might be irradiation, there might be kinetic energy of charge carriers, the electrons and the ions, there might be energy of neutrals, either by charge exchange collisions or if you think about sputtering from the collision cascades in the sputter target and so on. There might be exothermic chemical reactions, recombination of atoms or charge carriers, and of course external heating. On the other hand, the cooling parts are again radiation, mostly in the infrared, heat conduction and convection depending on the gas pressure and the design of substrate holder. There might be desorption, the particles take energy away. Endothermic chemical reaction, sputtering and secondary electron emission. Also these particles cool down the substrate or the electrode, and of course external cooling. And now the task is to measure this integral energy influx and to compare these measurements with the different contributions to the energy influx. And there exist several methods to measure the energy influx. For instance, spatial gradient. You can do that if you along the substrate holder or along a substrate you have different thermocouples, then you measure the spatial gradient, and by calibration you get by dt over dx, so the spatial variation of the temperature, the energy influx. What we are mostly using is what we call the passive thermal probe. We just measure the temporal slope of the temperature, of the surface temperature, and get from this the power or the energy influx. Another method is what we call the active thermal probe. We just heat a probe to a certain temperature and we know the power for this heating, and if there is an additional influx from a plasma or from an ion beam, then you need less heating power for the probe, of course, to attain the same temperature, and this difference is then immediately a measure for the incoming power. And we used also small test particles, special fluorescent particles, where the fluorescence is temperature dependent, and by calibration from the fluorescence, the comparison of the fluorescent lines, we can estimate the temperature of these test particles or probe particles, and from that we get the energy influx. So there exist several methods, and I just want to cite Noah Hershkovitz, why this energy influx is important. He said plasma processing characteristics are similar when only a limited number of plasma parameters are identical at the plasma wafer sheath boundary. Identical values of energy flux and particle concentration result in identical rates. So that means if you want to scale up your equipment, or if you want to compare one plasma source with another plasma source, so this energy influx from the plasma to the surface, to the substrate, is a very good quantity or similarity parameter in order to compare these equipment. And finally, the energy coming to the surface together with the momentum coming to the surface by the interaction at the end result in the energy influx and the equilibrium temperature of the substrate, which again affects the elementary processes at the surface, like the adsorption, the diffusion at the surface, the thin film growth, chemical reactions, and so on. So this is an interplay, and therefore this really is a key parameter to compare it. And now to the method. I will not go into the detail with the equations, but if you measure the integral energy influx, and this integral energy influx, it's the energy flux density integrated over the area of the substrate or the probe, for instance, and these incoming flux, as I mentioned, a sum of all these contributions, the kinetic energy of neutrals, of electrons and ions, of condensation, of recombination, and so on. And all these contribute, and you can try to find for each of these contributions an equation. So for instance, if there is a film growth, then the condensation of the deposited material is one contribution, and this is related, of course, to the deposition rate and the density of the growing film and the specific heat capacity of the growing film. On the other hand, if you are interested in the kinetic energy of electrons, here in the case of a Maxwellian distribution, of course, then you have to get here's the flux density of the charge carriers, and that's the mean energy of the flux carriers integrated over the energy space. And for the ions, you may take the Bohm criterion as one approach, and then you have to multiply it with the mean energy, which is given by the bias voltage, and the bias voltage is a difference between the substrate voltage and the plasma potential in principle. You can try to put equations for all these contributions, and then you have to sum it up, and on the other hand you measure these integral energy influx by these probes, as I mentioned, and then you can get information about this interaction between the surface, the plasma, and the surface. So this is the active thermal probe, just shortly to show. It's in principle a kind, it is 5 × 5 square millimeter, and it's a kind of a PT100 or PT1000 element used in the vice versa direction. And then what I mentioned, you have here this jump in the power for heating the probe, which immediately tells you the incoming power. Here's an example from a project which we had together with other groups in the ESA project. There is a stage where we have thruster. We characterize different thrusters, for instance, micronewton thrusters or gridded thrusters. And there is a lot of diagnostics on that stage, and one of these diagnostics is the thermal probe. And you can see here we heat the thermal probe to about 350 centigrade, and we need for that about 600 milliwatt. And then here we switch on the ion beam, the thruster, and then we just need to attain this temperature about 50 or even less milliwatt. So that means the difference is the incoming power from these thrusters. So we can scan that, for instance, here the radial profile of the thruster in different operation regimes and at different power densities. So it's really very simple. The other probe, which is even simpler, is the passive thermal probe, and we use that in many different plasma environments, in ion beams, in microwave plasmas, RF plasmas, magnetron plasmas, even in atmospheric pressure plasmas, in jets and dielectric surface barrier discharges. It looks something like that. This is the probe. It's a kind of a dummy substrate, and we just have to measure plasma on, plasma off, or ion beam on, ion beam off, and it's very simple. Textbook first year. You have to take the time derivative of the temperature, and if you have the difference of heating and cooling curve multiplied by the heat capacity of the probe, then you get the incoming power. It's really very simple. And my students, they did it very well with a lot of electronics for data acquisition and fitting the curves. So in principle, it's sufficient just to evaluate the kinks, the heating kink and the cooling kink, to get these derivatives, and as demonstrated here. And then at the end, you get a value, for instance, 1 watt per square centimeter. So this is an integral value. All these different contributions are in this value, but this is really measured rather simple for the plasma. Of course, you have to calibrate, as I mentioned, if you want to have absolute values, to calibrate the heat capacity of the probe. You cannot simply calculate because it's rather small and there is a thermocouple and all these things change the heat capacity. So we calibrate ultra high vacuum stage where we have electron beam, and we know of course the electron current and the voltage or the potential between them, and so we get immediately the heat capacity, which can be calibrated and then can be taken for calculating absolute values. This is an example in sputtering, so-called DC magnetron sputtering and high PIMS magnetron sputtering, high impulse sputtering, and you can already see the difference. It's at the same pressure, at the same power. Average, it's 500 watt, I guess, was here, and the pressure was about 0.1 Pascal, something like that. And you can see here, this is in a DC sputtering mode. Here's the target, the magnetron, and you can see the typical argon glow. Huh? And then here, this was a copper target. In the high PIMS mode, you can see this green light already by your eyes. It's the copper, excited copper lines and copper ion lines. And why? In the short pulses, so this is a DC, that's clear, and the high PIMS, there are short pulses, and the power going to the magnetron is in these short pulses, and then there's a pause. You see here the length of the pulses and the frequency, and that means in these pulses is a much higher density, power density at the target, and there are much more metals are sputtered and ionized and excited. Yeah, and that means you deposit more metal ions than metal neutrals. This is important for the heat, for the film properties of the growing film. Yeah, but in average, even the deposited energy, here's the thermal probe, might be lower because only the energy is coming in the pulse, and then it's a cooling pause. And in integral, if you make an average about the energy influx in the high PIMS and the DC sputtering motors, this might be lower. And here you can see if you grow films in a DC mode or in a high PIMS mode, then the grain size of the growing film is different, the adhesion of the growing film is different, and the density of the growing film is different, which makes it quite interesting for special applications. And here we just took this energy flux measured by this passive thermal probe in a radial scan here beneath the magnetron, and this is for the DC motors and this is for the high PIMS motors. And even if I said there are more, it was 100 watt and 0.5 Pascal, and even the energy influx in the high PIMS mode is less, you can see. It's about 70% compared to the DC mode. Just in the pulse, it's very high, but our probe can only measure the average energy flux from the plasma to the surface. That means the thermal load in case of high PIMS is less. This might be interesting for polymer substrates, thermally sensitive materials. So, and then we map with our probe the space in the chamber where you put substrates. So you can see here it's a very homogeneous energy influx. Somewhere here is the magnetron. So you put, of course, or localize the substrates in this region where you have a homogeneous energy flux and also homogeneous deposition at different places. So this is the energy influx. I said 70% of the DC in the high PIMS, but the sputtering rate is even lower in the high PIMS mode because it's only sputtering during the short pulse, then it's a pause, then the next, and so on. And in the DC sputtering, you have always sputtering. So that means the deposition rate is 50% of the DC. But that means if you divide that, there's about 150% of the energy influx per particle, per deposited particle in the high PIMS motors. And this is one of the reasons why these films are much denser and there's much better adhesion of the films to the substrates. Yeah, but at the end, in average, it's a less energy load or thermal load of the surface. So that's really very interesting. Of course, if you change the bias voltage of the substrate or your probe, then you get a curve like in a Langmuir probe. Here this is the ion branch and here this is the electron branch. So if you increase the negative voltage, you increase the energy of the positive ions, either the argon or the metal ions, and there is an increase in the energy influx. The lowest point is at the floating potential. This is the measurement, and we made a very simple model, but here in this model only the kinetic energy of the charge carriers, their recombination, and the secondary electrons is taken into account account, and you can see there is a gap between the measurement and the model, and this is due to the neutrals. There is sputtering, and also the neutrals, they bring energy to the surface. But this has not measured by the probe, and it's almost constant, of course, so that the flux of the neutrals are not affected by the bias voltage, of course. So then this is very simple. You make this simple model, you take the model and compare with the measurements, and then you know immediately that the difference in the energy influx, in this case, is coming from the neutrals, from the growing film, from the plasma. This is a method to get more information by this very simple method about the different contributions. Another example before I come to the ion beam for a plasma surface interaction is the so-called PIII. This is plasma ion immersion implantation. So you have a glowing plasma surrounding a cathode, and the cathode is a tool, for instance. This is often used in plasma nitriding. So nitriding of steel or of titanium for special applications, for instance in the artificial hips or artificial knees or something like that, which is of titanium, and there's a titanium nitride layer, and this is produced by these nitrogen implantation. And so you have a glowing nitrogen plasma surrounding the cathode, the substrate. This is what we know, and then there is a very steep, suddenly a very steep negative voltage pulse to the tool, maybe minus 10 or minus 20 kilovolt. And then you create, most of you should know that from plasma physics, a so-called matrix sheet. Then if you have these very steep negative pulse, you blow immediately away all electrons out of the sheath, and the ions, because they have much less mobility and higher inertia, they stay in the sheath. So for a certain or for a short moment, for a short time, you have just only an ion sheath. That's a so-called matrix sheath. And then also the ions see after a certain time this negative potential, and then they are accelerated and implanted into the surface. And then these glow, the sheath has to recover, and then the next pulse is coming in order to implant the particles from the glow. Okay, this is the principle of the PIII. But you can imagine during this high voltage pulse and the high implantation and sputtering by the ions, a lot of secondary electrons is released at these process. And we were interested in measuring and to get information about the secondary electrons in this process, and we did this by our thermal probe. So we varied the distance, and we could also rotate our probe to see the angular distribution, and it was far away. It was not in the glow, it was 20 centimeters or so far away from the cathode, and that means we can measure then only the coming secondary electrons, which are coming from the cathode with a rather high velocity. And if you would expect, if you turn around the probe minus 90 or plus 90, then you don't see the substrate, you don't see the secondary electrons. If it is 0, then you face to face to the substrate or the cathode, then you have the highest influx. And if you increase the pulse voltage or the pulse frequency, of course, then you have an almost linear growth of the energy influx. That's what you would expect. And this is just caused by these secondary electrons. And even what is more interesting is we used as a cathode a magnesium cathode or a magnesium tool, and which is oxidized, of course. But then we measured an energy influx of about 90 milliwatt per square centimeter, and suddenly at about, in this case, 50 minutes after operation, there is a jump, a huge jump in the energy flux, 10 milliwatt per square centimeter. And why? This is here the, let's see, poisoned or oxidized target, oxidized cathode, and during the operation of the plasma and the ions, it is cleaned, the oxide is removed, and then we have, after a certain time, pure magnesium, a metallic cathode. And then, you know, the secondary electron emission for magnesium oxide is about an order of magnitude larger than for a clean or for metal magnesium. You can see here in the jump. And then again, we started to let nitrogen into the chamber, and then slowly again the energy influx increases due to the increasing secondary electron emission for magnesium nitride in this case. Okay, I have shown you now two examples in surface treatment like sputtering or PIII, and I just want to come to the ion beam sources. You know that much better than me. The is the broad variety of ion beam sources. The main classes are still the Hall thrusters and maybe the grid, electrostatic gridded thrusters like the RIT system, which has been used many years ago at Artemis. But these ion beam sources, we had a strong collaboration with the colleagues in Leipzig, are also often used not only for base propulsion but also for surface sputtering and surface treatment, for instance in ion beam figuring, for very smart treatment of lenses for special astrophysical applications or optical applications and so on. So this is called ion beam figuring, where these sources are also often used. So here is our ion beam source. This is here the source. This is a microwave antenna and an ECR. Here's the power supply and here's the chamber. And I want to show you just a movie or animation. Now we are looking into the direction of the beam, into the plasma chamber. This is now an animation. You can see here the grid system, the electrostatic grid systems. Here's the microwave antenna. Here are the permanent magnets to increase the effect by the ECR effect. Then we have here the microwave energy deposited, the magnetic field, and the electrons are gyrate around the magnetic field lines, and from time to time they hit an atom, an argon atom, and ionize an argon atom. So we have a certain percentage of argon ions, and these argon ions, which are located here in a donut-shaped ring, they are accelerated by the grid system into the chamber. Yeah, so here somewhere can be the probe or the substrate, or if you put this on a satellite, then you have a propulsion. Now this is a real photograph. This is the plasma shape, and now the ions are coming into your direction. And if you interact these ion beam with a surface, this should be a model of a surface, then of course there will be implantation or sputtering or reflection at the surface, and it depends on the mass ratio, on the energy of the incoming particles, and the angle of the incoming particles, of course. So the so-called sputtering yield or reflection yield, it varies, depends on different conditions. For instance, if you have another angle, you have different sputtering cascades and you have different reflection and sputtering of particles. Okay, this is well known, and so we could make different or several experiments with the ion beam source. Here's the source, the grid system. Here somewhere is the substrate or the probe. For instance, the thermal probe, the passive thermal probe. We can change the beam voltage. That means we change the kinetic energy of ions. We can change the distance, the pressure between the source and the substrate. So that means we affect the charge exchange collisions by the distance or by the pressure. We can have an additional substrate voltage and so on. We can change the microwave power. So, and you would expect, if you increase the beam voltage, you increase the kinetic energy of the ions, then you will also measure an increasing energy influx. That's clear. And even if we give an additional bias voltage to our probe, then we can still increase the energy of the incoming ions. So for instance, this blue curve, it's minus 100 volt, it's plus to the beam voltage, so then even you can see it's a higher energy influx by the particles. This is in a certain distance here of about 20 centimeter, and of course if we are doing that in another distance, it might change. This was for the axial profile. I come back later, but what is even more interesting is the radial profile of the beam. And so we took our passive thermal probe and measured the radial profile of the beam. In an ideal beam, it should be rectangular, of course, but it is not ideal. And you can see, as you expect, if you increase the beam voltage, you increase the power, the energy flux in the beam, of course. That's clear. It's in a certain distance of maybe here 20 or 30 centimeter. And then you should think, if these are only ions, then you know the energy of the ions and you know the flux density of the ions, the current density, then you can simply calculate these profiles. And so we measured the energy flux density by Faraday cups and multiplied by the mean energy, and we get these profiles. And as you can see, there's a factor of 2 to 3 smaller, which is measured by the Faraday cup than by the thermal probe. And why? This is because our chamber is not an ideal chamber. The ground pressure is not so low. There is a certain background pressure, so there are charge exchange collisions on the way of the ions from the source to the probe. And then we get fast neutrals. And our thermal probe measures both the fast neutrals and the ions, the fast ions. But the Faraday cup only measures the ions, of course, the charged particles. So this difference is due to the charge exchange collisions, and that we could also see in another interesting experiment. This is in the setup. Here's the ion beam source. The ion beam is directed upwards, and then we put into the beam a stage with test particles or with probe particles. So there's a kind of a salt shaker. We inject microscopic probe particles into the beam, into the direction of the beam, and we illuminate these particles by a laser fan, as you can see here, and by a camera we measure the trajectories of these particles. So this is the idea, and this is what we call the vertical ion beam experiment. Okay, it looks something like that. I hope you can see that. Here is the ion beam source. Here somewhere is the bottom, and you can see here the falling particles, the falling test particles. And from time to time you can see here they are reversed, so they describe a parabolic trajectory. So the test particles, we used hollow cathode glass spheres. The mean diameter was about 90 or 100 micrometers, as you can see here. And this is the idea of the experiments. If there is no ion beam, then there is acceleration by the gravitational force, like Galilei told us. And you can see that by the stroboscopic illumination of the particles, the distance between the particles, just the acceleration. But if we switch on the ion beam, then you can see the particles are accelerated, then they are decelerated, and then even they go back, they are accelerated back. You can really see that. And this is just, of course, due to the ion beam, to the momentum transfer by the ion beam. So that means the ion beam can balance the gravitation or even overcome the gravitation for these particles. And so if we, these are the triangles, if we measured this net force, then we compare that again with the force which we calculate by the Faraday cup measurements only for the ions, and you can see again there is a factor of about 2, and the green points are the measurements from our thermal probe, where we take into account the neutrals and the ions. And of course also these test particles are affected by the ions and the neutrals. It doesn't matter for them if the momentum is transferred by an ion or by a fast neutral. And there's a quite good accordance. And that brought us, or brings me now to the other diagnostic, the force diagnostics. Here again, what I told you about the charge exchange collisions. If here is the source, near the source we have 100% ions. But far away we have almost no ions. All these ions are undergone charge exchange collisions, and the profile, the ions is this, and the profile of the fast neutrals is this, and this is the sum of both. And if you compare that with the measured ion density by a Faraday cup, then you can really see this is this profile. You can see this axial profile for the ions. But if we measure by thermal probe or by this force probe, I come back, then we measure this profile, which is a sum of the neutrals and the ions. And then again we have to take into account the geometry of the whole of the grid system. It doesn't matter, but what is important here is the ratio between the length or the weight of the particles and the mean free path for charge exchange collisions. And even by such simple measurements, if you put the probes or the test particles at different distances, you can determine the mean free path for the charge exchange collisions in this experiment. It's very simple. And then we thought, it's nice, can we also check that by a force probe? And our first approach was a very simple force probe. It's a kind of arm or cantilever. Here's the target. The ion beam is coming from here, and we used a kind of an ampere meter where we had to compensate the bending or the angular movement by the current. And so again we could measure this, what we call the beam pressure, the force by the beam particles, and again we get a profile what we measured by the thermal probe or by these small test particles. Okay, I come now to these force measurements, and this is also triggered by interest in sputtering and description of sputtering. If you have an incident ion, then you may have sputtering depending on the angle, depending on the mass ratio of the projectile and the target atoms, and depending on the energy, of course. So that means at the end you may have either a reflected ion or you may have sputtering at the surface. And there exist a lot of codes to describe this process, like SRIM or TRIM or TRIDUNE and so on. They are very well known. In principle, these are Monte Carlo codes, so binary collision codes in that, and is much known about sputtering yield and the energy of the sputtered particles. But what about the energy of the reflected particles? What about the angular distribution? What about the momentum transfer and the ratio between ions and neutrals in such processes? And so the idea is, again, very simple, and I like simple, nice experiments which can be done in a master thesis, for instance. So assume we have a target which is not fixed, it is a floating target, and then we have an incident ion, and then there's sputtering. Yeah? Let's say copper. Here, one incident ion sputters 3 copper atoms, as an example. Then, of course, in order to the outgoing particles and the incoming particles, there is some momentum transfer, and at the end, there would be a certain direction of the momentum which could move the target due to this momentum transfer, the interaction. And if we fix now the target only in one direction, that means in a vertical direction but not in a horizontal direction, then we don't measure really the effect of the incident ion, but we measure the effect of the sputtered and reflected ions. And then at the end there's a projection of the momentum in the x direction or radial direction. Then the target would move into this direction just due to the reflection or sputtering of particles at the surface. And then we took this idea now at Christmas time. That's very common in Germany, what we call the Christmas pyramid. And you know, these petals are moving due to the convection of the hot air. Yeah, there is a reflection of the gaseous molecules here in the hot air, and by this momentum trend it starts to rotate the blade. That's nice in Christmas time and simple. And that was the idea, can we do that measurements also in the ion beam? So, and then there was a master student, he constructed a kind of these, we call that spin, sputter propelled instrument. So there should be very small friction on a needle. The petals are the targets, which can be changed in material, and in the angle can be changed. And then if it starts to rotate, we measure just by a laser diode the speed of the rotation, the angular acceleration, for instance. So that was the idea of this experiment, and this is how it looks in reality. And now, yeah, it is here located on a needle. Here's the diode, the laser diode, and that's put into the reactor, and something here on the bottom is the ion beam. So the ion beam is coming into this direction. And this is now a real-time movie. You can see here the spin, this instrument. Somewhere here at the bottom is the ion beam source. You see already some light from the ion beam source. There's a plasma, of course, but the beam is not switched on at the moment. And I show you this experiment. You see it's still on, and now the beam is switched on, and it really starts to rotate due to the effect of the ion beam, especially due to the sputtering reflection. This is really, now it's switched off, and then it's deceleration of this instrument. You can see here measurement by the laser diode, acceleration and deceleration in the ion beam. And if you plot that, it's a perfect curve, as you know from the first year in mechanics, due to the angular acceleration. And if we know now the moment of inertia of this instrument, which has to be determined independently, of course we did, and then we can measure the torsional moments of that. And if we know that, by these torsional moments, we just measure the acceleration, the speed of acceleration, then we get the force which drives the rotation of this spin instrument. And please remember, this is just due to the reflected and sputtered particles. It's not due to the incident ions. The incident ions would move the petal into this direction, in the vertical, but we only measure the movement in the horizontal direction. So this is just due to the sputtered and reflected particles. So again, we can change the experimental conditions, for instance, the distance between the source and this instrument. We can use different target materials. We can use different ions here in the chamber or in the ion source. We can change the distance and the ion energy and even the target angle. Of course, and then we measure these, and if you would expect, if you increase again the beam voltage, that means the kinetic energy of the ions, then you get an increase in the force, and this is the measurements, the black points, and the red points are the calculated measurements by this trim code. And of course, the trim code takes only into account the ions, not the neutrals, and if we take into account the charge exchange collisions, then we get a quite good accordance between the measurement and the model. So you can change the ions and you can change the target materials. Again, this is for copper and this is for graphite. As you can see here, for graphite, the force is much lower due to the sputtering. Of course, if you take argon ions, then the sputter yield for carbon is or graphite is much lower due to the mass ratio as for copper or for titanium, for instance. That you can simply see in the measurements. And if we take that all together, we get here the sputtering plume and the plume of the reflected particles. And both are contributing to the momentum which we are measuring by the spin. So it's a nice instrument and simple experiment in order to compare or to validate such sputtering codes, for instance. So on the one hand side, we have the experiment, we measure the angular acceleration, and by Newton's law, we get the torsional moment and the force, what we call the force by this measurement. And on the other hand, we can calculate, even if we take into account the charge exchange collisions, we can calculate this force by the trim code, and so we can really compare both the measurements and the model. I'm coming to the end now with these force probes, and so this is a nice experiment, of course, but you cannot use it in industry or in an ion beam source. It's just in the lab for nice experiments. So better is to use a force probe which is related to what you know, these thrust measurements. So that's just a kind of a pendulum, and the first approach was here again, we measured the displacement due to the action of a particle beam, of an ion beam with such a pendulum, which we measured the angle by laser diodes. And so we put this on a platform, on a stage here in our chamber. Here's the ion beam source, and we can move it axially and radially in order to get the axial and radial distribution of the force. And you can see here, this is the radial distribution and the axial, and again you obtain the same results as before. This is the measured force by the probe, and this is the calculated force by the ion current. And again, there is a discrepancy which increases with the distance, again due to the neutral particles, to the charge exchange particles. And even Alex, he took a target of different regions where he could calculate it for each region the contribution to the force or to the momentum transfer. Here is the ion beam, and here he put a force probe, and then he turned this target and he calculated for each part of the target what is the contribution to the force of the reflected or the sputtered particles. And so he could see that for different materials. As you can see here, the highest sputtering is for silver and copper, of course. For carbon or graphite is rather slow. And if you look about the angular distribution, again, you get not a maximum at 45 degrees, you got a maximum at 60-70 degrees, which is related to the what is known from the sputtering angular distribution due to the crystal structure of the metal. And then we improved this method, this mechanical thrust measurement, by an interferometric probe or interferometric force measurement. So again, we have here our target where the ions or the sputtered particles are incoming, and the bending of these ceramic tube can be measured very sensitive by interferometric method. So we can really measure bending of a few nanometers that can measure the force in a sub-micronewton regime, sub-micronewton. As you can see here, beam is on, beam is off, beam is on. We can see here the displacement here in micrometers, for instance, is a rather large force, and from that again we guessed the influx from the particles, the effect of the particles. You see there is a lot of oscillations, of course, due to the mechanical properties of the system. We have an eddy current break in order to reduce currents and to get a fast signal. And then now we put this probe, this new interferometric force probe, again onto the stage in order to get axially and radially resolved measurements. And here is this cantilever, here is the target, and you can see as a mirror, and we have two mirrors, that means two sensors, two interferometric sensors, so we even can get the vector, the thrust vector, you would say, if we put that into the ion beam. And now fix it for a copper target and for a fixed energy of about 1200 eV. And if we turn the angle of the target, of course, then we get here the signals of the both sensors. That's just a consequence of the geometry. So we can get the information. And now we measure the signal or the angle of the bending due to the incoming ions and due to the sputtering in dependence on the angle of the incoming ions, as you can see here. And if all ions or fast particles from the beam would stick at the surface, then we have a momentum transfer of 1. Then we would have here a perfect line, the angle would be the same. But if there is reflection or sputtering of particles, then you have the transfer of 2, and it's something in between, and that means a deviation of the measured curve from this line is a measure for this number of reflected and sputtered particles, as you can see here. That can be measured for different conditions and compared with SRIM, again with SRIM calculations. And if we take, for instance, here what we call a carbon velvet, this is an almost perfect absorber for ions. It's a black body for ions. You see, this is a kind of carbonaceous needle structure. That means there is no sputtering and no reflection. All particles are incoming, they stick here into this target material. And you can see this is this green triangle. This is almost at the line. So there is just all ions are coming and sticking and can be measured. So this is a perfect material for just measuring the incoming ions, the beam ions. Yeah? But if you take silver or copper, you have a lot of sputtering, a lot of reflection. And if you compare that, these measurements with the simulations, there is a quite good agreement between them. And then the last step, and this is the last 2 slides, is now what I mentioned so far is we put the force probe here as a kind of a thrust measurement here in the beam, direct. We measured so far the direct effect of the beam particles, but now we placed the force probe here surrounding the target. So we can now change the angle of the target and also the material of the target, and we measure by the force probe now, of course, only not the direct ions, but the sputtered or the reflected particles from the target. This is how it looks like. Here you can see the target, and here you can see the rotating or turning force probe. And now we measure what I mentioned, the reflected or the sputtered particles. You can see here the situation. This is the ion beam. This is the angle of the target related to the normal of the ion beam. And this beta is the angle of the force probe turning around the sputtering target. And we made a simulation again, the simulation for incoming ion angle of 45 degrees. Again, for this beam voltage or energy and for this argon 65 millipascal. And you can see here the contributions of the reflected and the sputtered particles and the direct bombardment. Of course, if you are below 45, there's no direct ion influx to this probe, only flux due to reflected and sputtered particles by the target. And so we compare that with our measurements for different ion beam energies, 300, 600 and 1200. And you can see again there's a quite good agreement. Of course, if we come into the region of 45 degrees, then that means the probe is going into this direction. That means the probe can see not only the particles from the target, they can see the particles from the beam. Now there is a steep increase, of course. These are the primary or the direct ions from the beam. But here the ions or charged neutrals coming from the target due to sputtering and reflection. I'm coming to the end, and I would say I want to bring a little bit more closer to you these 2 diagnostics, the force probes and the thermal probes, which can be a supplement for other diagnostics like mass spectrometry, optical emission spectroscopy, Langmuir probes, and so on. So these non-conventional plasma diagnostics, they can give some information about the energy influx and finally the substrate heating due to the plasma operation or plasma influx, and on the force transfer due to the momentum flux by particles from an ion beam or from a sputtering target. And this has been done by these passive thermal probes and by these interferometric force probes. But again, these can be only a supplement. You should not forget the other diagnostics, but they can give very simple, on a simple experiments, additional information, and they can give also information about the neutral particles. This is often not so simple to get information about neutral particles, but the force probes and the thermal probes can give these information. So the main people are doing these experiments are Mattis and Thomas. Here is this Hybex experiment where we have the stage in the chamber, and thank you very much for your attention.